Hi, how are you? Hope all is well. We'll wait a few minutes and then I'll introduce you to everyone and then the stage is yours. It's like around 5 minutes, then the room will
Sure.
start.
Okay.
Hey everyone in the audience so far. We'll wait like 2 more minutes and then we will start the room. Thank you. And whoever wants to come up and ask questions later on, please raise your hand and we'll have our interactive discussion. Thank you. Thank you, Guta, for letting me know. I heard my sound was very low, so I hope it's better now. I hope you can hear me now. Thank you. Okay, thanks for coming and welcome to the Science Society. I just wanted to thank everyone, and especially a special thanks to Dr. Sharon Schwartz, who offered to give a talk about his very interesting and important research. So, yeah, let me introduce you to Dr. Schwartz. He is a physicist and a senior lecturer in the physics department at the University in Ramengan. He is primarily interested in quantum optics, biphoton generation manipulation, and the theory of nonlinear phenomena. He received his PhD from the Technion Israel Institute of Technology under the supervision of Dr. Mordechai Segev. His thesis, Nonlinear Optics in CZT, researched new effects in a family of cubic nonlinear crystals. This led to the profound discovery that under certain conditions of light illumination and applied electric fields, a class of material, cubic crystals, becomes highly polar and greatly modifies its properties. Before his PhD research, Sharon received a Bachelor of Science from the Technion, and the Technion Institute awarded him the Applied Materials Fellowship, as well as the Miriam and Aaron Goodworth Fellowship for his exceptional achievements. In addition to this prestigious award, Sharon is the recipient of the Technion Award for Excellence in Teaching in recognition of his work as a teaching assistant. He spent as a postdoc his postdoc time at the Stanford University in the lab of Professor Stephen Harris, and he has a lot of publications in very prestigious journals such as Applied Physics, Letters, Physical Reviews, Letters, Nature, Optics, and Optic Express. So, yeah, this is very impressive, and thank you so much for being here. For us, and it's morning, and for the West Coast, it's very early. So our members that are more from that side of the world are excited to hear the recording later. So thank you so much, and the stage is yours.
Great. Thank you so much for the very kind introduction and for having me. This is a very good opportunity, and I'm very glad that I can share my research with you. And so I'll try to explain and give you some background, and then, of course, everything will be open for an open discussion. Yeah, all right. So let's begin. Maybe I start with saying that the work that actually I was invited to speak about is a part of a bigger project that we have, and this project, the goal of this project is to try to use a technique that is widely used for different type of imaging processes, mainly what started with visible light, but now we try to extend it into X-rays, and we think that X-rays could benefit a lot from this type of technique because imaging is a very challenging task with X-ray, and I'll explain what I mean by saying this is a very difficult task. So the technique is that I'm going to talk about is basically called computational imaging, which is part of the title of this work. And the idea of computational imaging is essentially to use computational methods, right? It uses computer assistant method to do that, to do imaging. And one of the so the idea here usually, okay, let's start from the very beginning. What we usually do, and everybody almost nowadays basically use a camera. I mean, you have in your cell phone or any other, that you want to take a photo of something, either of your friends or yourself or some or a mountain that you want to take a picture of. So you do it very easily. You do it almost naturally without paying even attention to that. You just taking your cell phone, you're aiming at your target that you want to take a picture and take a picture. But what's really happening there when you take a picture? So when you take a picture, the light that is either scattered or transmitted depend on the configuration. So if you usually take a photo from your friend, so usually the light hits at your friend's face and then goes to your the optics of your camera, and then eventually it hits a detector. And this detector is made usually of pixels. And the role of the pixel is basically to translate the distribution of the light that is related to the object into an image. Okay, that's basically, and so the distribution of the intensity is will be mapped into basically a map which we call an image, and this reflects the object, right? But in between, you have the optics, and the optics mainly contains lenses and maybe other optical component, but mainly lenses. And with visible, that's very easy. You can do imaging of very small object on very big objects. That's actually very easy, and people make it for many years now. Very good lenses. But if you take it into X-ray, this has become very difficult task to use lenses for various reasons. And actually, they're not just technical; they're also really fundamental. So this action of taking one point of your object and transform it into one point on your detector, it's extremely difficult to do with X-rays. And that's basically the whole thing about the motivation of using computational imaging. And to replace all this optic, what we do, we replace all these optics with most sophisticated scheme, which I try to explain right now and in a second. And we don't need lenses. Okay, that's basically what we do. So if you, for instance, you just look at this nice image that I see now on this app, this is kind of it's an example of one of the mask that we use. So what we do, we take a mask. It is basically, the mask it's a mask that, as you can see here, there are some area along this mask, dark area and white areas. So basically we have a pattern, and this pattern is imprinted into the beam that later will um, irradiate your sample. So instead of taking, usually what you do, you take a uniform beam, and then you take and then you put behind your sample, you put a detector with pixels. What we do, replace the pixel, we don't put a pixel. What we do is we take a single pixel detector, so it means that we take one pixel, a detector that collects the entire radiation without any ability to distinguish where it's exactly arrived from. But instead, we put the mask just before the object, and the intensity at the detector will be just proportional to both, to the transmission of the mask and to the transmission of your object. And what we do, basically, we correlate between the pattern of the mask to the pattern of the object, and from this, by what we really need to do is to move the mask, as you can see here. We move the mask, and we repeat this process for many different patterns, and eventually we kind of given a score. So if the pattern of the mask it's really correlated to the pattern of the object, you get a really high score, high intensity at the detector. If the correlation is poor, you get low intensity at the detector. So eventually you can use it and make some computational algorithm that you can recover your object from this kind of an exercise. Okay, that's basically, and these people call it a computational method, since you really rely on computational schemes, and eventually you can recover your image by doing this way, and without any lenses at all, and without the need of a pixelated detector. Okay, so this is something we've been doing for a couple of years now, and we realize we have some advantage of this. And one of the advantage of this method is related to the other thing, which is really computational, is what's called compressive sensing or compressive imaging. So compressive imaging is really something that's related to compressive storage when you want to save the amount of data you want to use a zip file, or you want to use you want to save a memory if you have on your computer when you after you took the picture, and now you have an image, you have a file that contains it. Now you want to make it a smaller file, just to save memory. And the way you do it, right? I mean, if you think about your cell phone camera, it contains many pixels. Because why? Because you need the high resolution, because you don't know exactly where the variation of the intensity of your image will be really sharp and where it's going to be not sharp. For example, just think about a field with a tree, and maybe there are also some skies around it, right? So very near the tree, of course, there will be the image, the variation in the image are very sharp, right? Because there is something happening there. The field turns into the root, or then to the leaves and all the details of the tree. But if you look just on one spot of the sky, it's not very different from a different spot on the sky. But when you design your camera, you need to make the number of pixels. Now the number of pixels is getting to something like, maybe 15 or maybe 20 million pixels nowadays. Really many pixels. And the reason you're using so many pixels, because you don't know exactly which event will occur exactly what position of your image. But once the image is already taken and you want to save it, now you don't really need all this type of information, because some of the pixels are carry information, and some of the pixels actually carry the same information as the pixel around them. Okay, so maybe it's not so important, and you can recover the image without them. Okay, so that's what you do, and that's why you have, if you use a JPEG format, for instance, you will find out that the memory size that you use those type of format is much reduced with compared to the original format that you use. So the idea of compressive imaging is very similar. We're using kind of these patterns of this mask, which are kind of random. And then what we know, again, we know that we don't really need that many number of patterns, but we scan randomly. And we're using a similar type of algorithm. And nowadays we also, not just we, but also other groups, also use artificial intelligence to make it even more sophisticated and maybe more efficient, okay? So that's the idea, and we're going to use it the same thing we're going to use for the second part of my talk that I'm going to speak about is how we're going to use it for the chemical element mapping. So this is one part of the talk. Now let's switch to the chemical mapping, and what is chemical mapping and what is it about. So and why it's important. Okay, so chemical mapping is all about is to identify what exactly type of atoms you have in your material. Think about a compound or a mixture of different type of atoms that you want to use. For instance, if you have a factory that produces stainless steel, you want to make sure that your material is really uniform across the entire material. Different portions of the material be the same. And one way to do that is to take just an image that is not just an image, but it also can provide you the spatial distribution of your atoms. And then if it's uniform, then you know that the material, the compound that you need is uniform. That's basically one example of the use of this chemical mapping. And it's actually it's quite used in many other fields, which is kind of interesting. It starting from fundamental science. So if you want to understand the many things that happening with material science, batteries, if you want to check the quality of batteries, and there are several types of other fun areas, such as even cultural heritage. What they do there, for instance, if you have or if you are a museum, or in your museum you have an old paint, that was made from a different type of materials, and nobody really knows, because it's kind of it's maybe 500 or 600 or 400 years old, and they use along the years a different type of material for paint. Basically, the paint were made from different type of chemical elements, and you don't and if it was damaged and you want to repair it, so what you would do, in a sense, you really need to know exactly what are the type of the chemicals that actually made this paint was made of, because otherwise you may try to use a more modern paint, and then you can introduce some chemical reaction that actually will destroy the paint that you want to repair. So what they do, they really go there and do this chemical mapping, and you find exactly the chemical components and everything, and then you know exactly what kind of material they use and what type of exactly atoms it was used to prevent from preventing damage. But there's many others, archaeology, and now also for forensic science, means trying uh, to find the chemical fingerprints of criminals. This is also something that people use, but many things like that. Okay, so how does it work? Okay, it's actually rather simple. And so if you think about that, so you shine what you do, well, the other type of method to do that, but with the X-rays, and that's the big advantage of X-rays, is that X-rays interact mainly with the electrons that are really close to the nucleus of the atom, very deep electrons. And by interaction with them, when they hit and the X-ray absorb, they kick out an electron from the input level of the electron. They just kick it out from this atom, a process that we call ionization. Okay, that's why we call X-ray are considered to be ionizing radiation. Okay, so this is an advantage, because if you think about a molecule, then in the process of creating the molecule, or basically creating the molecule and sharing the molecule, is only the outer shell are involved. The core electron, they are really close to the nuclei. They are really tightly connected to the nuclei, so cannot share the electrons. The inner shell electron cannot be shared between the different atoms that comprises the form the molecule. So if the outer shell of molecule, the outer shell electrons, of course, have a lot of advantage. They are very interesting, but they do not preserve the properties of the atom, since they are involved in the molecule, and they are mostly influenced by the other atoms that shared in the same molecule. So if you want to find what is the atoms that this material is made of, you must look at the core electron, the one which are not participating in forming the molecule, because that's what you want. Okay, so and that's what you do. So you shine with an X-ray, and the X-ray has a unique signature of the fluorescence. The fluorescence process is, again, as you shine it, you radiate it with an X-ray, the atom, and it kicks out an electron, and another electron from another shell now take the place of the electron that was kicked, and since it's usually coming from an upper level, it goes down to the deeper level, and in this process, when the electron takes the position of the electron that we just kicked out from the atoms, it radiates, the atom radiates, and this is called fluorescence. Now, what's special about this with X-ray fluorescence is that a unique signature of this fluorescence. So in other words, any material, any atom will have a different type of emission lines, which we can detect by looking at the photon energy of the wavelength, which is the same thing, of course, and we do that by using detectors which are sensitive to the photon energy that is emitted from the atom, so we can identify that. Not just we. This is a known process and widely used, and that's why X-rays fluorescence can be used to identify the chemical elements in the material. And of course, if you want to get the spatial distribution, this is not enough. You need to get the spatial distribution. So in most cases, what people have done before our work, they actually try to focus the beam. So what they did, they just focused the beam to a relatively small spot and put the detector. So every time you just illuminate a small portion of your sample, and you just record the fluorescent data from this area, and then you scan with you usually scan the sample. So every time you illuminate a different small portion, and eventually what you do, you just compare between the different radiation from the different spot, and eventually you can reconstruct your map. The problem with this process is, first of all, is it's relatively slow because you really have to go a point by point. This is one thing. And the other thing is that it's not so easy to use, even to focus with X-rays. It's not so easy when you go to higher photon energies, or, well, shorter wavelength, which again is the same thing. Since it's very difficult, it's become a very difficult task to focus. So that's become very, very difficult. And what can you gain by going to very high photon energy is basically looking at basically heavier elements. The heavier the elements, the higher photon energy you need to go in order to look at its fluorescence. Okay, that's basically the so. If you think about heavy elements, I'm not talking about those very rare radioactive materials, but also gold is very basically very heavy. In some sense, also iodine, which is a material that people use for many different things, also is not it's relatively heavy and not so easy to measure with conventional methods and many others. So it's not something very rare. It's kind of a big challenge for this type of thing. Okay, so basically what we have done in this work was to combine between these two different fields. One of them is computational imaging with single pixel detectors, and the other one is X-ray fluorescence. So we replace usually the in our detector, what they do, we collect, instead of collecting the transmitted radiation through the objects, we collect the fluorescent data, and but repeat the same process I just told you at the beginning of my talk about this computational method. And we collect the data, and we can reconstruct the image for each one of the emission lines, and from that we can identify the atoms, and from that we can basically eventually construct the chemical map. Now, the main advantage of this method, I think, is it's much faster. It does not require, with respect to a more conventional method for chemical element mapping, it does not require any lens, and to make it much easier to implement and much cheaper. A typical X-ray lens can cost several thousands of dollars, and the mask that we used in our case was a sandpaper, just for the comparison, which probably you can get as many as you want for a few bucks, right? I mean, okay, maybe some other cases you need maybe a more sophisticated mask, but it's, again, most of the masks we can get you can buy for maybe tens of dollars or something like that. So it's much cheaper, much faster, and in principle no problem. In our case we were measuring up to something like a 20 kilo electron volt, and usually you want to go maybe to double or 3 times more than that. There's no basically no fundamental limit in contrast to use of lenses. So that's basically the big thing. I think about that, it's really opening now new opportunities for different fields, as I said, to look for much higher, much heavier elements. It also opened new opportunity to use three-dimensional, because the penetration depth of X-rays, if you increase the photon energy, become larger. And for three-dimensional imaging, what you need is really to go inside of your material as much as possible. So with our method, is basically possible, and that's actually something we have already started working on. Try to extend these two-dimensional methods into three-dimensional to get something like computational tomography of object by using this type of effect, or basically method. And I think that's more or less what I would like to tell you about here, without getting too much into detail. But yeah, and I think it's. I would like very happy to get any question from your side.
Yeah, thank you so much. That was very informative. Yeah, if anyone has questions, please go ahead. Eric, do you have a question? Okay, maybe he's not he can't speak right now. Yeah, this is really amazing. Do you have already applications for this technology? Like, what do you think is the first application you want to go to?
So there are several directions here. Some of them already, X-ray fluorescence is actually heavily used in many industries, starting from petroleum industry to identify exactly what the ingredients, what the compounds, exactly what you get from the oil. Uh, but of course, we can do it much faster than the conventional methods. Some idea that we had is trying to take this into more things like medical imaging, because medical imaging is really something that people do at much higher photon energy than conventional X-ray fluorescence method. So one idea that we're trying to implement, I don't know. Well, it's too early to say whether we're going to be um, successful with that. But so if one thing that people already have been doing with mainly with computational tomography with CT, if you want to identify cancerous tumor, for instance, it's a very difficult challenge, because if you look just on plain X-ray absorption, the difference in the absorption between a cancerous cell and normal cells will be very, very small, and that's very difficult. So what people do nowadays, they add something they call contrast agents. So contrast agents are just material that absorb more X-ray than other material, and they tend to be more in the cancerous cells or the tumors, and this way people can increase the contrast of image, and that is make it easier to distinguish between what is cancerous and what is not cancerous. Now, if you take but still, it's still a difficult task, because even with the contrast agent like iodine, that actually is very popular for many different type of cancers, they still measure the absorption difference, and the contrast is still low. So you actually sometimes miss, situation where you could say that this patient had cancer, but you still miss it. And with here, if you look at fluorescence, instead of looking at absorption, and we can actually use the same material, so we can use the iodine, for instance, but instead of looking at the transmission of the ion or absorption of the iodine, we can look at the fluorescence of the iodine. So the fluorescence of the iodine, the contrast would be huge, because there's no, if the main problem is that usually you look at in the body of the patient, so there are many organs, right? I mean, so the cancerous organ is very, very small portion. Um, so the absorption is kind of the total absorption. We want to distinguish between two different you know tumors that are actually embedded in some much larger body, which contribute also with many scattering mechanisms and absorption. And with here, well, if you can inject this contrast agent only to the cells, the cancerous cells, and only them will basically radiate, then your contrast will be huge. So that's that's I think that's something that we could be very interesting to do.
So I also understand that your method is way faster, which for brain imaging is quite important. So would you be able to perform brain imaging with this technique? Does it go through the skull basically?
Well, yeah, well, we need to work out the details, but basically, yes, because we can work at wavelength that will penetrate through the skull. The Yeah, well, the thing is that the fluorescent that emits the material that will emit the fluorescence should also be something that designed to be able to know to penetrate the skull. There are several ideas, probably not iodine, but something maybe like gold is a good. People already trying to use gold nanoparticle for many type of imaging, but that's something that maybe something we can consider. But maybe the answer is maybe.
Yeah, interesting. And yeah, also I was thinking that would you be able to, so you would be able basically to see cancers at a very early stage because your imaging is way more detailed. Um, so that would be a really great breakthrough, I think.
Yeah, I hope so.
And I read in the article about your research that this would also be really important for scanning methods for art. How is that? So I don't know if you considered that too, um, or would it be more for a dating from when an art piece or historical piece is from?
Yeah, well, maybe, yeah, it's I think maybe. I mean, all the options you mentioned are possible. This is a very early stage. I mean, we just introduced the method. We really need to try it and to really understand. Because any new method has limitations, right? Um, I would like to be optimistic at this point, and I hope there's a great potential. But let's see.
Go ahead.
Hi, thank you, Katrina, for doing this room, and thank you for giving me the opportunity to come on the stage. Thank you, Sharon, for being here. So, how I just read the abstract, so I'm trying to get a grasp of the application. So, how will this technique or this new advance be useful in uh, improving the resolution of structures, molecular structures, for example, a viral particle or molecular machine like the ribosome or the ATP synthase or any of those smaller molecules? Thank you.
Okay, so thank you for your question. So right now, okay, so in principle, when you think about X-ray fluorescence, the spatial resolution is limited by the ability to focus the beam. Uh, if you can focus it really small, you can see very small objects like maybe well, nobody think well. No, it depends. Let's talk about sizes, right? I mean, so a single molecule is probably very difficult to see because that is really you need to get a very very small, very high resolution. So even with focusing, that's not really possible. In our methods, what the hope right now is to get to resolution of about maybe a tenth of a micrometer. So everything that you can think about in this regime any object with this that require resolution of that kind, we probably can do. That's kind of the hope. I don't think well, it's going to be very challenging with this type of method to do much higher resolutions. But even that, it's really a big achievement. This is the other advantage of our method, because conventional methods just rely on your focusing capability. In our cases, we can do much better than the focusing capabilities. So yeah, I mean, I hope I'm answering your question, but that's basically the limitation. In terms of concentration, that's something we don't know. This depends on the sensitivity, and we still need to test this.
Yeah, thank you. So to rephrase my question, uh, what my understanding of your answer is that it does have its limitations. So in that case, let me rephrase my question. What would be the most useful application of this advance in which particular context?
Right. So, well, the most, I don't know the most, right? I mean, it's very difficult and have to be careful with the most. Um, I think that the really opening of three-dimensional fluorescence type imaging, of chemical imaging, right now is a really bottleneck for many industries. Even try to monitor many processes, of fabrication and the production of different type of compounds. That could be a big issue for industry. Medical imaging, we really can do what we want to do to make it more sensitive to different type of health problems. That will be another, I think, big step. Uh, Probably these are the two that I have right now in my mind. But if you ask me in a year or something, maybe we'll find something more. Or who knows?
Yeah, go ahead, Imran and Lauren.
Yeah, sure. I'll just go ahead. Thanks,
Yeah,
Katerina.
sure, Lord.
All right. Hi, Sharon. I do have a question that is connected to the previous question in terms of the applicability of this fluorescent mapping. Now, I know that typically chemical and elemental mapping, they normally use very advanced analytical tools, to characterize those contents, especially if you're looking at a sample or a product and you want to get to proper characterization. I do have in terms of the fluorescent mapping, I do have some concerns associated with the applicability, especially in the engineering industry. But I want to get an understanding based on your technical expertise of what some of those limitations are in the engineering industry. How do you think, like I do, that there are specific limitations in the engineering industry? I just would like to know your perspective on Dr. Schwartz.
You mean the limitation of our method, or in
Yeah.
general of the X-ray fluorescence?
Well, I think with specific focus on the imaging fluorescence tool,
Okay.
because I think it should be very applicable in the engineering industry because we deal with a lot of composite materials. But I don't see it. I mean, I haven't necessarily seen technological developments in this field, and I'm trying to figure out why there hasn't been a push in terms of advancing this level of mapping. Because like I even personally deal with a lot of composites, and we've never seen the need for this level of imaging, and I probably would want to know why from your perspective.
Right. Okay. So I'm not an expert, in industry industrial applications. Of course, I'm professor at university. So, but to my understanding, and really tried. Okay, so it depends, right? I mean, it depends on the sensitivity. Well, the applicability of a method depends on the advantage of the method, and in this case is probably, I guess, the sensitivity um, and the resolution. But also, I think you always have to uh, consider also the price of the devices. These devices aren't cheap. I think typical. Well, I don't have this one, but from what I know, what I heard, is we're talking about a machine that cost several $1,000. Sorry, no, no, I'm confusing myself. It's probably on the order of maybe 20 or 30, $1,000. That's probably the price of a machine, of a simple machine. There are more complicated machines, and of course, I guess in the industry, people just do this math, or whether they really, this really going to improve, the process or whatever they want to use. And if it's eventually economical consideration, not just the engineering advantage. Um, but I know, I'm aware of many industries that use it. I mean, that's I guess not. It's not profit, not good for everyone. But I guess if your process is very expensive, or if you really lose a lot of your material because of the process, then probably you want to use something like that. But if it's something that is probably the process is cheap, maybe just too expensive for that.
Thank you, Dr. Schwartz.
Yeah.
Imran?
Right. May I, if, sorry, I didn't want to speak over anybody.
Do you want to go ahead and ask, or?
Are you talking to me?
Yes. Do you want to ask a question?
Oh, right. Okay. Yes, yes, yes. I've read about your tool, and I'm deeply intrigued in exploring new markets for it, and also understanding the medical background for this. I also read that you are, as we speak, actively involved in therapeutics as well. Correct me if I'm wrong.
Okay. Can you just raise your voice because I couldn't hear you?
Right. Is it any better?
Yeah, much better.
Right. I was driving, so I can listen to myself very clearly with the air conditioning on and the windows closed. So I thought the whole world could hear me, and I was so wrong. So, anyway, the thing is that I've read about Dr. Katerina's tools and the fact that she's perhaps working on therapeutics as we speak. So I just wanted to understand that, is this so? Are you working in the direction of developing medications for mental health challenges? Is that right?
Yes, I am, but today is about Dr. Schwartz research, not about mine so much.
Right,
So
right, 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 right. Okay, I'm
yeah,
sorry. Yeah,
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 but
yeah.
thank you for your interest. I appreciate it. Um, I wanted to ask Dr. Schwartz, do you think your technology is also something what could use for information technology and communication? Um, yep.
Yeah, so I thank you for this question. So people use similar ideas in communication. That's not something we invented, but there are similar ideas in communication. That's right.
Well,
Oh,
since I'm
interesting.
driving, I'm sorry. Since I'm driving, I will not be able to open any links and read. Could you briefly fill me in on Dr. Schwartz's research, if you don't mind?
To give a short summary, okay, Dr. Schwartz, do you want to give another very short summary? And then, yeah, if you want.
Okay, so this is going to be very short. Okay, that's all right. So yeah, just briefly. So the idea here is that it's a new, well, it's a method. We develop a technology that what it can do very fast chemical element mapping, which means we can tell you exactly uh, which atoms, which types of atoms you have it in any area of your of an object. We do it by using X-ray fluorescence, and we developed a method that makes this everything here, all this method much faster than more conventional method that people use nowadays. And one of the advantage of our method that we don't need lenses like other methods, and this why we can extend the method to much higher photon energies, to take it to open new applications such as three-dimensional imaging, and um, and also medical imaging, which is also something that people don't use X-ray fluorescence for this type of application these days. So
Oh,
this was
this is
like.
exactly what I was thinking of from a medical imaging because I have a healthcare background. So I used to work for a pharmaceutical, and I have obviously I used to eat, sleep, drink medical science once upon a time. I do think a little differently now, but not entirely in opposition to medical science, but in conjunction with. I believe in like as a scientist, you would probably agree, both of you, that the object of life is to improve, and you can only improve by learning and by applying logic and rationality and deductive and inductive analysis. These basically are that's it. That is how we can harness the mind to propel us to the next level. So having said that, medical imaging, especially X-rays. So what you're saying is that I mean, right now X-rays are definitely not 3D. So they're just one-dimensional. And for 3D, you end up using MRIs, CT scans to some extent. One could argue in their favor. Well, MRIs perhaps more so, but obviously MRIs, and I know this more so because I have to go through at least 4 or 5 MRIs every year because I have a debilitating neck condition, spondylosis. It's terrible, so 3, 4 levels. So obviously my doctors need to see what is happening to my discs in real time, and 3D imaging is the best. X-rays don't serve the purpose. So I would often discuss with radiologists at depth in depth that what could possibly be there, like in terms of perhaps more narrowed imaging, in terms of different levels, applying different levels of energy and contrast into the X-ray to get it. But what you're talking about, if I understand it correctly, is applying computational algorithms that are able to piece together the X-ray into a 3D model. Am I right in my understanding of what you just said, or am I totally off
So
track
okay,
here?
let's be okay. Let's not talk. I will not take all the credit for everything. So computational methods, of course, computational tomography. People, have been using for many years with X-rays, right? This is the CTs, right? What we do is, I think we have a method. What we propose basically here is a new method that can increase the contrast. So we, in some sense, increase the sensitivity of the methods. And the computational part here is coming to save radiation and to make the measurement more efficient, basically.
So basically, it's you're playing with the image itself and also how the image is taken. So the angles and the level of energy applied, because I think there are so many variables within the X-ray apparatuses out there that you can play with. But I really don't think that they're actually being played with to the extent that they could be, because well, it's this is what it is. I mean, whatever has the limits of research that we have, we stick to it. So there's not much exploration in that area, if I understand it correctly. So I think you're kind of pushing the boundaries there.
Well, we're definitely trying to push the boundaries. That is correct. We are not alone. I mean, for fundamental science, there are many, many different ideas. Um, uh, and the idea is, right now it seems that, to me, you know, um, one of the things that people have not tried enough is to really take all the information that you can get from the X-ray scans, and that's what we're trying to improve. A lot of information, so we already shine your body with X-rays, so we know it's ionizing radiation. So it's better to make this type of it's better to make your measurement efficient if you already have to do that.
I think that'll be nice. I mean, from one angle, I could see that this could lead to, like, the benefits of your technology could be in the ER. Like when you go to the ER, like if there's an accident victim or something of that sort, right? Broken bones and whatever vertebrae, etc. And if there is a more enhanced medical, like imaging technology available, and cost effective as well, then very quickly, especially in developing countries, you could get a, I would say, as accurate a picture perhaps as an MRI, but at least something close to it. So I mean, like, it's all about diagnosis. So the doctor knows at least whatever the hell's going on inside the ball, whatever. So if you have a more accurate, your treatment methodology, whether it's surgical, invasive, non-invasive, etc., those decisions would tend to be more, perhaps, tailored to the need of the patient.
Yeah.
So you have, like, you've patented this, or this is, or like you said that others are working on this with you, or I mean, like, not with you, but in general, like, right?
No, no. So there are different type of new directions in science. We are very at a very early stage. We're also looking in this, we this direction, into this direction. It's very early, I have to be honest. Unfortunately, people will have to wait until we really can come up with a real machine that you can, we can. I don't know. We probably not. I'm a physicist, so I'm working in fundamental science, but I would love that people, more engineers and people that really knows how to work on this type of machine will take our ideas and really make device from them.
Hey, hello.
Somebody wanted to
Oh yeah,
speak,
hi.
so.
I have a question about your method. So I understand the X-ray fluorescence is basically mostly a surface method because the X-ray fluorescence actually here only a few keV, so they don't penetrate that long. You mentioned that the 3D. Are you meaning that you want to mapping the 3D chemical elementary elemental distribution of the surface?
Okay, thanks for the question. I mean, yes, you're right. I mean, in this work, we couldn't penetrate that much, but now we trying. One of the efforts we actually working on is trying to working at the photon energy that actually penetrate more inside. So the idea is probably more like to think about three-dimensional to see the surface of the object that going to make the fluorescence, but they are going to be probably inside, underneath the surface of an object um, that has lower absorption. That's why the fluorescence can emerge from the entire object. So one example of this, you think about, as I think I tried to mention, if you think about the problem of the computational, computer tomography. I mean, you can inject or other means you can inject, for instance, kind of material like iodine, and this iodine, would just goes propagate, just through your blood vessels. So if you want to see the three dimension of the blood vessel, yes, the surface of the blood vessel, right? But this blood vessel is already inside the three-dimensional body of the patient. So in principle, you can see exactly how the blood vessels are distributed in the body, and I think we can do it very efficiently. So this is kind of an example that I have in my mind. What I mean by three-dimensional.
Oh, so you need a like higher energy than the iodine at KH,
Yeah,
then so that's like, but iodine X-ray is like 130
yeah, yeah,
something.
yeah.
It's like it goes like a few millimeters before. I mean in human body, how much? I don't remember exactly. A few millimeters of penetration depth.
I think it's slightly more than that, but yes, I mean that's in the human body. I think maybe, well, I don't remember exactly, but I think it's slightly more than that. But it's not. Yeah, it's not the. It's would be iodine would be very difficult to do. You know. The whole body, but just beneath the skin, or just slightly more than that. Yes, you're right. The penetration depth will be the limit. So if you use iodine, I don't remember. I think it's 1 or 2 centimeters. Uh, but if it's less than this, but if not iodine, you have other materials. Uh, uh, well, they will have to be non-toxic, of course. I mean, you cannot inject toxic, something which is toxic to the human body. But already people talking about, for instance, about gold nanoparticles. This also could be a good candidate, and gold will be much higher photon energy, and the penetration depth is going to be much greater. Uh, People already use barium, which is slightly higher than iodine. It depends. Well, exactly what the application that exactly the area you want to look at.
Frank, if I may, I am aware. I mean, and correct me if I'm wrong. I remember from my healthcare industry days that iodine has been used for a long time in X-rays to get like more phased imaging of tissues and blood vessels as well. On the other hand, barium has also been used for analyzing things like esophagitis and
Yeah.
gastroesophageal reflux disorders. So different elements have been used to play around with X-ray imaging. So iodine has been, in my opinion, I think it has been, to my knowledge, it has been used for quite some time in MRIs as well as X-rays.
Yeah, I agree. Yeah, iodine is for contrast imaging. Is it enough for imaging thyroid, like without adding extra iodine?
Can you say again?
I mean, thyroid has more iodine
Uh-huh.
concentration. It's close to
Oh,
certain.
you mean
Is
just
it like do you think it's sensitive enough without adding contrast, you can imaging organ like a thyroid?
that's an excellent question. I haven't checked. I don't know. I don't know the answer. Yeah, no, I don't know. But it's if so, it would be really great.
Oh, also I read briefly. So you are using like a point detector, only one element, one pixel. How about do you actually need many move the detector to image at different locations?
So this is also possible, and this probably will even can speed up the measurement as well. Yeah, I mean that's something that we actually considering. So yeah,
I didn't get. I mean, I didn't read exactly how do you what's the procedural steps? How I mean you have to I mean my question, how do you have to move the detector around the object
oh, that's
in
what you
order
mean.
to?
No, what we do have this mask that we put before the object, and we move the mask instead of the detector. Detector just collects all the fluorescence. The fluorescence is indirectional, it's non-directional. So it doesn't matter if you move it or not, as long as you can, as you collect. Your detector can collect, the fluorescence. But we do need to move the mask, and that's probably take some time, but we can do it really fast.
Great, thank you
Okay,
so
thank
much.
you. Oh, that's good. So how about if we have a actually 2D detector, does it help? I mean, helps, but it's not that useful. I mean, it's 1D detector already good enough. I mean, not 1D, 1 point, one pixel detector.
For fluorescence, basically, there's no meaning of using. Yeah, I mean the point detector or the 0D detector is good enough, because there's no the fluorescence will be to any direction, so there's no really point in doing that as long as we're using this mask.
So the mass moves in 2D.
Yes.
Okay, yeah. How many? Oh, but how many realists? I mean, do you stop and shot and you need to take many papers?
Yeah.
You have some number, right? It's a few hundred.
So that's exactly where the computational and compressive sensing is coming into play. Um, there are many algorithms nowadays. In principle, without any tricks, it will actually quite long process. For any pixel or pixel equivalent, you will have to take one measurement. But since we know how to play with these tricks with the compressive sensing, we can really save a lot of measurements. The record right now, not something we've shown in this paper, but the record from other research is something about a compression of a factor of 1,000. So instead of doing a million, if you need a million pixels, you would need a million measurement. But we can compress it to about 1,000. That's right now what can be done. That's eventually this will be a limit of the method. You cannot do as many as pixels as you want because your patient will not wait that much.
Great. We have been speaking for an hour. Thank you so much for giving us the time and sharing your knowledge and your research with us. And thanks everyone for your questions. Really appreciate it. And I hope you come back one day with more updates and maybe projects to share. Thank you.
Yeah, thank you for the opportunity. Thanks again.
Great. Thanks everyone in the audience for being here, and enjoy the rest of your evening, I think, Dr. Schwartz.
Yeah.
And nice seeing you, everyone, and come back. And I'll close the room in 3, 2, 1. Bye, everyone.